Good evening, all. Good evening, esteemed colleagues, respected guests, and dear participants. I, Dr. Snehika Shrivastava, Co-Coordinator, FDP, on behalf of IPS College of Technology and Management, feel honored in welcoming you all on the second day of one-week faculty development program on recent advances and applications of manufacturing in Industries 4.0, organized by IPS College of Technology and Management Gwalior with the support of AICT ATAL scheme. This program stands as a testament to our collective commitment to professional growth, academic excellence, and fostering a community of lifelong learners. So we are proceeding of third session of 6 days faculty development program. I invite Dr. Meghanshu Vashishta, Professor IIT BHU Varanasi. But before his speech, I take this opportunity to present bio sketch of Professor Meghanshu Vashishta. Sir did his BE in 1997 from Engineering College, Kota, Rajasthan University. ME in 2000 from IIT Roorkee. PhD in 2010, Indian Institute of Technology, Kharagpur. Sir did his postdoc in 2012 on material characterization from Newcastle University, United Kingdom. Sir has 22 years of teaching and research experience. Sir has got BOYSCAST Fellowship from DST India in year 2010 and Fellowship Fast Track Project under Young Scientist Scheme from DST India in year 2011. He has 26 publications to his credit in last 3 years. He has one Indian patent on an ultrasonic vibration assisted minimum quantity lubrication grinding system to his credit. Sir has published 2 books. Sir has guided many research projects and some are going on. I invite Professor Meghanshu Vashishta to deliver his talk on micro-characterization of material upon machine. It's over to you, sir.
Thank you, Dr. Snehika. I am delighted to receive the invitation from IPS College, as well as I am also thankful to Dr. Manoj for giving me this opportunity for this lecture in this FDP. So I am going to share the screen. The screen is visible?
Yes, sir, visible.
Okay. So the topic of my talk, I have intentionally opted as micro-characterization of material upon machining because nowadays in the new industrial era or industry 4.0 scenario, if we consider, then it is very much necessary to characterize the material at micro level because nowadays we are going for micro manufacturing, we are also going for nanotechnology. Similarly, we have also opted micro characterization of material for improvement of quality. And I have also opted this topic for machining because if we consider the machining operation contribution in manufacturing, then it is very large. So the topic of my talk is micro characterization of material upon machining, and this slide is having a figure. That figure is a indication of a signal that we will discuss during the presentation of this lecture, that this signal is very important for micro characterization of material. Before starting of micro characterization, let us discuss about a very important term, that is quality control. What is the role of quality control in manufacturing and why it is necessary to go through this? Quality control in manufacturing is judged by microstructure state of the material, micro hardness variation from the surface to the core or to the subsurface level, surface roughness of the workpiece, phase analysis of the material that has been produced by the manufacturing process, as well as nature of residual stress. Intentionally, I have kept red color for nature of residual stress because this factor, among other factor of quality control, is very much important for quality of manufactured product that we will see. Now, if we think about a manufactured product, then we can judge the quality by its microstructure state, its variation of hardness from top surface to the subsurface, surface variation, roughness variation, phase analysis, and nature of residual stress. So we can say that if we want to judge the quality of a manufactured product or a manufactured component, then we have to assess all these parameters to check whether the quality of the produced component is okay or not. And we are having various conventional techniques for assessment of quality under these parameters. We are having optical microscope that will assess the microstructural state. The cost of this microscope is around 15 to 20 lakh, and generally it takes 1 to 2 hours for assessing the metrology analysis. Micro hardness tester is an instrument that is used for micro hardness testing. Its cost is also around 15 to 20 lakh, and if we consider the time to assess the micro hardness, then it is also from 30 minutes to 1 hour. Roughness tester is used for surface roughness. It costs 3 to 10 lakhs, and we generally take 10 minutes time to use this instrument for assessment of surface roughness. XRD, that is X-ray diffraction technique. It is very, very important technique for phase analysis and assessment of residual stress. The cost of this basic equipment, I repeat, the cost of this basic equipment is around 1 crore, and it takes 1 to 2 hours. Approximately 55 minutes is generally taken for 5 scan of a material. So if we consider the cost of all these equipment, then it will be around 1.5 crore. And the total time taken for assessment of quality control, it is more than 2 hours. And if we provide 2 hour time for assessment of quality control of a single product, then it is not feasible to use 2 hour time for assessment of quality control. So what is the answer with us? The answer with us is micromagnetic technique that is used for microcharacterization of material. This single technique, I repeat, this single technique is used for microstructure state characterization, microhardness variation, phase analysis, and nature of residual stress can also be assessed by this single technique. We have seen that these state or these quality control parameters are assessed by separate techniques or separate instruments in conventional method. But this single technique is used for assessment of quality control, as well as the main advantage is this: within 5 minutes we can assess the quality of the manufactured product. And the cost of equipment is also low. It is available in market within 15 to 20 lakhs. This technique is used in case of manufacturing. What is the definition of manufacturing? If we ask, it is conversion of raw material by some value addition into a useful product. So what are the various manufacturing process? We can classify the manufacturing process in 4 categories, mainly 4 categories. First one is the forming, second is the metal addition, third is the melting and solidification, fourth is the metal removal. This fourth category I have intentionally put in bold category. What is the role of this bold letter in this? Because the contribution of metal removal is 60 to 65%. It means it is very important pillar of manufacturing among all these classifications. Metal removal process can be characterized or can be divided into various categories like turning, shaping, planning. You have seen. You are also familiar with drilling, milling, broaching, gear manufacturing, thread cutting. And the last operation that I have written, it is grinding, that is in blue color and bold font. Why I have kept this in blue color? Because among all these metal removal process, or I can say among all the manufacturing process, grinding is very important because it is used for surface finish improvement. And all the manufactured component, whether it is coming from welding shop or whether it is coming from forming shop or casting shop or machining shop, it will definitely go through grinding operation. So grinding is very important last tooling machining operation that decides the quality of manufactured product. But unfortunately, what happens, this figure is indicating that in case of grinding, sparks are there. Sparks indicate that large amount of heat is generated in this last machining process or in this last tooling process. So this spark is not desirable. It is indicating large amount of heat, and this large amount of heat is not good for quality of the component or the produced component, because this large heat will damage the microstructure, it will damage the surface roughness, it will also damage the micro hardness variation. So this heat is dangerous or detrimental in the process which is called finishing operation. Why this heat is generated in grinding process? First, we have to see into this. In case of grinding, a grinding wheel is used, and this grinding wheel is having various abrasive grades. These abrasive grades act as a cutting tool. In case of all machining process like drilling, in which drill bit is used, in case of milling, in which milling cutter is used, in case of turning operation, a single point cutting tool is used. All these process used a cutting tool. So in case of grinding, grinding wheel is not a cutting tool, it is having abrasive grit, and these abrasive grit act as a cutting tool in case of grinding. But unfortunately, what happens in case of grinding? We are using abrasive grit as a cutting tool, and we are not able to control the geometry of these abrasive grits. What is the importance of geometry? It is very much relevant with the generation of spark. We all know that if we are having a circular workpiece and a single point cutting tool, then this is the schematic of this workpiece and single point cutting tool. This single point cutting tool is just having a surface over which the chip will flow. The chip will flow over the rake surface, and this is the rake surface that can be indicated here. To define whether the rake angle is positive or negative, we have to follow some principles or some basic rules. What are those rules? First, we have to draw a direction. That direction will indicate the cutting velocity. So in case of this figure or in case of actual turning operation, exactly at the point of contact between the workpiece and the cutting tool, we have to draw a tangent, and this tangent will indicate a direction of cutting velocity. Then if we introduce a perpendicular plane, if I introduce a normal plane that is perpendicular to cutting velocity, then this plane will be known as reference plane. So we are having rake surface, we are having cutting velocity, we are having reference plane. And these are very much required to define whether the rake angle is positive or negative. If we rotate the rake surface, if we rotate the reference plane towards the rake surface, I repeat, the fundamental is rotate the reference plane towards the rake surface. If this direction of rotation is clockwise, then we can say this rake angle is positive rake angle. So in this schematic, if we rotate the reference plane, it is clockwise direction. So this angle is positive rake angle. And if we are having another schematic like this, in this case, if we repeat all the fundamentals that we have discussed now, then first of all, we have to draw a tangent at the contact point. So here in this figure, at the contact point, if we draw the tangent, then this is the direction of cutting velocity. And if we introduced a plane that is normal to cutting plane, then this plane will be reference plane. So in this figure, this reference plane has been introduced exactly at normal to the cutting velocity. Now, if we repeat the same process or same rule, then we can come to know that whether it is a positive rake angle or negative rake angle. So in this figure, if we rotate the reference plane towards the rake surface, then what will happen? This direction of rotation is anti-clockwise. Since the direction of rotation is anti-clockwise, so we can say that this is negative rake angle. So what is the utility of positive rake angle and negative rake angle? In case of machining, we can control the geometry of single point cutting tool by providing positive rake angle or negative rake angle. How this positive rake angle and negative rake angle affects the machining? So, suppose this segment is indicating a chip and this chip is flowing over the rake surface, and in this case, this tool is positive rake tool. The V1 is the velocity of chip segment before machining, and I am considering that after machining the velocity of chip is V2. So what will happen if we machine this workpiece material by a positive ray cutting tool? Then considering the V1 is equal to chip velocity before cutting and V2 is the chip velocity after cutting, I am considering the mass of chip as m, small m. So I can write that mv1 is equal to momentum of chip before machining, and mv2 is the momentum of chip before after machining. If I consider machining by negative ray cutting tool, then what will happen? In this case, this will be the flow of chip, and v1 is the velocity of chip before cutting or before machining, and v3 I am considering it is chip velocity after cutting. Here V1 and V3 are velocities in case of negative ray cutting tool. So if we consider change in momentum in case of positive ray cutting tool, the change in momentum will be mv1 minus mv2, and the change in momentum in case of negative ray cutting tool, it will be mv1 minus mv3. So always this term, that is change in momentum in case of negative ray cutting tool, it will be always higher than machining with positive ray cutting tool. So this is indicating that amount of cutting force is large, very large in case of machining by negative ray cutting tool, and that is not desirable. Large cutting force are always generated in case of machining by negative ray cutting tool. In case of machining, one important fundamental is this, that always the cutting tool should make contact exactly at the diametric plane. Why the cutting tool should always make contact with the workpiece at diametric plane? This is also very important aspect that is related with the tool geometry. So if we consider that the cutting tool is having contact point exactly at the diametric plane, then this is the situation. And in this case, the angle is positive rake angle. We can see that pi-r plane or reference plane, when we will move it towards the rake surface, it is clockwise direction. Rake angle approximately it will be around 10 degree. And when the cutting tool is making contact above the diametric plane, what will happen? If we plot the cutting velocity and if we plot the reference plane, then this rotation will be more. So when we'll rotate the reference plane toward the rake surface, the value of rake angle will be different, but it will be positive. So we have changed the rake angle from 10 degree to 15 degree by keeping the position above the diametric plane. And let us see what will happen when we are having the position of cutting tool below the diametric plane. Suppose this is the location of cutting tool making contact with the workpiece surface below the diametric plane, then in this case, this is the direction of cutting velocity exactly at the contact point. If we draw a if we draw a tangent, then this will indicate the direction of cutting velocity. Now, if I introduce a normal plane to this cutting velocity, then this normal plane is the reference plane. According to fundamental, I have to rotate the reference plane towards the rake surface. If I rotate this towards the rake surface, then this angle will be negative because the direction of rotation of pi r plane towards the rake surface is anti-clockwise. So this rake angle is negative. So I have been given a cutting tool. The tool geometry is indicating that the rake angle is 10 degree. But if I change the location of this single point cutting tool over the workpiece surface, then I will change the rake angle of cutting tool, and that is not desirable. So always we have to keep the contact point exactly at the diametric plane. Now, what will happen in case of grinding? Suppose this is a single abrasive grid, if we consider, and this rectangular is box is the workpiece, then at the contact point, this grinding wheel is rotating and abrasive grit is making contact. So if I plot a tangent, then this is the direction of tangent, and this is indicating the cutting velocity. And this normal plane is indicating the location of reference plane. And the chip surface is the rake surface. So we can say that if we rotate the reference plane towards the rake surface, it is anti-clockwise. And this is indicating that we are machining with negative rake cutting tool. So in case of grinding again, if we come back with this schematic figure, we can see that the direction of cutting velocity is exactly at the point of contact, and it is having a reference plane that is indicated by red color. If we consider the surface over which the chip is flowing, it is the rake surface. So according to fundamental, if we rotate the reference plane towards the rake surface, then this direction of rotation is negative. I can say that the rake angle of this abrasive grit is negative. So unfortunately, we are machining or we are providing surface finish to the manufactured component by a cutting tool that is having negative rake angle, and this negative rake angle is highly negative. Whenever we are providing the negative rake angle, we generally keep the value of negative rake angle around minus 10 degree to minus 15 degree or minus 18 degree up to, because if we increase the negativity of rake angle, then definitely large amount of force will be generated and large amount of heat will be generated, and that is not desirable. But it is very much unfortunate that we are not having any control over the geometry of these abrasive grid, as well as we are not able to control the shape of these abrasive grid in case of grinding. That is why we are using highly negative abrasive grid in last machining operation, that is generating spark. And spark dangerous that we have seen. Now, what is the remedial action? Can we reduce the amount of cutting force? Yes, we can reduce the amount of cutting force. All of you have seen that when we start the machine, you have seen the starting of lathe machine, you have seen the starting of drilling machine, you have also seen the starting of grinding machine. What happens in case of grinding of these machines? In case of drilling operation, the rotational velocity of drill bit is very low. In case of turning operation, the rotational velocity of the workpiece is also low. But you have seen that when you start the grinding machine, the rotational velocity of the grinding wheel initially it is very high. Why we keep the grinding velocity so high in case of grinding? If we experimentally plot the graph between cutting force and cutting velocity, then this is the plot that have arrived from the experimental data. This is indicating that amount of cutting force will decrease if we increase the cutting velocity. And this is the case when we are having a positive ray cutting tool. Now, if we plot the graph for negative ray cutting tool, then we can say that at 1000 RPM, this is the magnitude of cutting force in case of positive ray cutting tool. And this is the magnitude of cutting force in case of negative ray cutting tool. But at higher RPM, 3000 RPM is generally starting or initial velocity of grinding. So if we start a process at 3000 RPM, then amount of cutting force is very low. That is why in case of grinding, we start the machining process at very high cutting velocity. This is a simulation video of a positive ray cutting tool machining and negative ray cutting tool machining. You can see that in case of machining with negative ray cutting tool, the large amount of plastic deformation of the workpiece surface is clearly indicating that large cutting force are generated during the machining. You can see the chip formation in case of negative ray cutting tool. It is having large serration mark at the top surface. This is indicating that large amount of force is generated in the machining with negative ray cutting tool. So this is not desirable. We have seen that in case of grinding operation, that is the last tooling operation, spark are generated and we cannot control the spark because the abrasive grid that we are having, it is having large negative rake angle, and this large negative rake angle produces a large amount of heat. This large amount of heat, it is transferred or transmitted during the machining. Various sources are there which are acting as a transfer media in case of this heat transfer. What are those sources which act as a transmitting media for transfer of this heat? Coolant is there, air is there, which transfer the some amount of heat. Some amount of heat will goes to the chip, and very small amount of heat will go toward the grinding wheel or abrasive grid. Why very less amount of heat is transmitting towards the abrasive grid? Because generally we are using abrasive grid as alumina and silicon carbide. These alumina or silicon carbide abrasive grid, they are having poor thermal conductivity. That is why very small amount of heat is transferred to the abrasive grid, and because of high thermal conductivity of the workpiece, large amount of heat is transferred to the workpiece. So you can see the large size of arrow. This large size of arrow is indicating that large amount of heat is transferred to the workpiece, which is also not desirable for quality control of workpiece, because it will affect or it will distort the quality, and the detrimental quality of the workpiece is not desirable for the customer or for the field application. This elevated temperature condition or grinding heat will induce grinding burn. It will also result into metallurgical changes, micro hardness variation, surface and subsurface crack, as well as this large amount of heat will introduce tensile residual stress in the workpiece component or the manufactured product. This tensile residual stress is detrimental. According to literature or according to the research outcome of various scientists, tensile residual stress is main problem in grinding, and that is not desirable by any customer. This tensile residual stress detrimentally reduces the static strength and fatigue life of the product. So, why this tensile residual stress is detrimental? Because suppose I am having this component, this is the component that I am having. If it is having some manufacturing process, and this manufacturing process is having compressive residual stress, that means the direction of residual stress will be compressive. It will compress the component. In that case, if the component is having, voids, if it is having porosity, if it is having cracks, so all these voids, porosity, cracks, they will be suppressed. Their size will be reduced because of this compression action by the compressive residual stress. But if the component is having tensile residual stress, then the nature of action of this tensile residual stress is like this. It will try to elongate all the things, whether it is porosity, it is void, or whether it is cracked. So it will try to open up, or it will try to enlarge the porosity, void, crack. So when all these will be enlarged, they will reduce the fatigue strength or the static strength of the component drastically, and immediately the component service life will be reduced and it will fail during the field application or during its intended service life. That is why we have to always assess the tensile residual stress. It is very much important in comparison to other parameter like microstructure, micro hardness, surface roughness. We can manage the surface roughness. We can play with the poor surface roughness. But if the component is having tensile residual stress, then it will be very much detrimental. We have seen that in case of quality control in manufacturing, we are having a last tooling process. In manufacturing, the last tooling process is having named grinding, and this grinding is having abrasive grit, which are having highly negative rake angle, and because of high negative rake angle, it induces heat, and this heat will reduce or will destroy the quality control or quality of the product, because this induces thermal damage in terms of induction of tensile residual stresses. These tensile residual stresses are very much detrimental as per the global industrial record or as per the outcome of research scientists who are working in the area of manufacturing. So, if we consider this block as a component and this component is having cracks at surface level, the component is also having void or free space. It is also having some porosity. So we know all manufactured component or any produced product is not 100% accurate because it is having all these imperfection or all these impurities. So if the component is having all these impurities and it is also having tensile residual stress, which will elongate the component in this direction. So what will happen with these cracks, porosity, or void? All these will get enlarged like this. You can see enlargement of crack, enlargement of void, enlargement of porosity. So when these get enlarged, they will detrimentally reduce the static strength and fatigue life of the component. That is why the trusses or bridges or other important structure, if they are having this tensile residual stress, they fail before their service life. You have seen in the news that there is a crack over the bridge, there is a crack over the trusses of the railway overbridge, there are cracks over the railway track. Why these cracks are coming? It is because of induction of tensile residual stress inside the manufactured product. We have to measure the residual stress, and a very popular technique and well-established technique is X-ray diffraction technique. This X-ray diffraction technique is a standard practice for measurement of residual stress. It provides absolute value in megapascal of the residual stress as well as the measurements are repetitive. That is the advantage of this technique, that measurements are repetitive. This technique is based on Bragg's law. What is the Bragg's law? We know that material structure is made of various planes. So the slide is indicating various planes, and we can indicate the distance between two planes as DO. DO is the distance or interplanar distance between two planes or two crystallography planes. So this DO or distance between crystallography plane is very much important. If I pull the component like this, then this D will become low. So this direction of elongation or this direction of stress or tensile residual stress, it will reduces the D interplanar distance. And if we compress the component, it will increase the D. So by measurement of D, we can assess the amount of residual stress. So this X-ray diffraction technique uses X-ray, and this X-ray measure the D whether it is increasing or whether it is decreasing. So by using this measurement of D and Bragg's law, we can calculate the amount of residual stress inside the component by this mathematical expression. But there are some limitations of X-ray diffraction technique. What are those limitations? The limitation is measurement time is higher. In case of X-ray diffraction technique, we have to usually scan the component at 5 different locations, and this 5 scan will take 55 minutes minimum. So we can say that 1 hour is minimum time required for scanning, and this time is very much high. This technique is a laboratory-based technique. We cannot take the instrument from the lab to the railway track or to the field application. So this is the limitation. We have to cut the component from truss or component from some bridge or railway track, and then take this component to the lab for X-ray diffraction analysis. This technique requires lot of amount of work, and the size of the component or the size of the sample is also very small. 35 gram sample size is required in the holder of X-ray refraction technique. The measurement depth of this technique is also very low. It is around 10 micron. This technique, I already told you that it is expensive. 1 crore is the basic X-ray refraction technique setup cost, and this technique is non-destructive in nature. Not non-destructive, it is destructive because we have to cut the sample. Now we are having a very good micromagnetic technique. The name of that technique is Barkhausen-Noyes technique, and this technique is having various advantage, or it is having various superiority over the established or popular X-ray diffraction technique. This technique is faster technique. You can scan, you can get the complete history of any manufactured component within 5 minutes. The depth of penetration or depth of measurement is also very high in comparison to X-ray diffraction technique. So we can assess more height of the manufactured, more depth of the manufactured component. The equipment is portable. The equipment is having a box shape. This box shape is having 7 kg weight. So you can carry this 7 kg weight in your hand to the field application, to the railway track, or to the railway bridges. And you can assess the quality at the field. And any complex shape can be analyzed, like gear tooth, like a spine shaft. They can be easily analyzed by this technique. And this technique is having the biggest advantage. It is non-destructive nature, so user-friendly technique. The Barkhausen-Noyes technique is based on magnetism. So let us go through the magnetism. The figure is indicating permanent magnet. We can see that magnets are having N and S. N is indicating North Pole and S is indicating South Pole. So we know the property of permanent magnet. In case of permanent magnet, magnetic line of force, they all come out from the North Pole and then they emerge into the South Pole. So this magnetic field is having a boundary. This magnetic field is having a boundary. In this boundary, the effect of magnetic field can be felt. Outside this boundary, magnetic field effect cannot be felt. So this is the iron component. If this iron component is away from the boundary of magnetic field, nothing will happen to this iron component. But if we have this iron component within the boundary, then what will happen? This iron component will be attracted towards the magnet. So this boundary is having name domain. This is having name domain or domain wall or magnetic domain wall. So now we can define magnetic domain wall or magnetic domain boundary is exterior of this magnetic field effect. We are having two type of magnet, permanent magnet and electromagnet. In case of permanent magnet, we cannot change the strength of magnetic field, but in case of electromagnet, we can change the strength of magnetic field. So if we consider a electromagnetic field, then it is generated by flow of current. Any flow of current will generate the magnetic field, and the direction of this magnetic field is always perpendicular to the flow of current. Suppose in this current is flowing, so this is the direction of current, and all magnetic field will be generated in this direction. That is the perpendicular direction to flow of current. So we can say that any flow of current will generate the magnetic field, but current is nothing. It is the flow of electron. So principally, we can define that any flow or any movement of electron will generate the magnetic field. And inside the material, we are also having free electrons, or these electrons are moving in an orbit around the nucleus. So if we go through the fundamental, then these electrons will also generate the magnetic field, because we have seen that any flow of electron, any motion of electron will generate the magnetic field. So will this flow of electron will generate the magnetic field or not? This flow of electron inside the material will generate the magnetic field. Can we see that magnetic field? We can see the microstructure of material by using the optical microscope. And nowadays we are having a sophisticated device. With the help of that sophisticated device, we can see the magnetic field. So we are having a instrument. The instrument is having name magnetoforce analysis. This magnetoforce analysis will see the magnetic field. So this is the actual image of magnetic field inside the material captured by magnetoforce microscope. So you can see this black color boundary is the boundary of magnetic domain, or it is the boundary of magnetic domain. And these domains or magnetic domains in that material are randomly orientated as captured by magnetoforce microscope. This is another image of magnetoforce microscope. You can see that these magnetic domains are randomly orientated. So this random orientation of magnetic domain is nothing but it is the stability criteria. They are randomly orientated like this so that they can nullify the magnetic field of their neighbor. If they nullify the magnetic field of their neighbor, then resultant magnetism is zero, and they can stay, or they can keep themselves in stable condition. But if I provide some energy, if I provide some force, or by apply some energy, then these magnetic domain will get energized. They will get energized by getting that energy. So in case of this last figure, if I supply some energy to this magnetic domain, then they will get disturbed, they will get energized. Again, they will try to get the stability. So how they can assess, they can achieve the stability? They have to align themselves in the direction of flow of magnetic field. So you can see that they all the magnetic domain they have aligned in the direction of magnetic field, and in this case they have assessed the stability. So there was some motion in the magnetic domain when we applied magnetic field. We can say that when we apply some magnetic field, magnetic domain will get energized, and this energized magnetic domains are in disturbed condition, so they will align by moving themselves in the direction of magnetic field. So one thing I want to highlight here, this is the motion of magnetic domain inside the material. Now, suppose I am having a ammeter here and I am having a permanent magnet here. There is no connection, there is no wire connection between this ammeter and this permanent magnet. If I move this permanent magnet towards ammeter, then the needle of ammeter will deflect. The needle of ammeter will deflect if I move it towards or away. This will indicate that this motion of permanent magnet is generating a voltage pulse. This motion of permanent magnet is generating a voltage pulse if I move it like this. This voltage pulse is again generated during the motion of this magnetic domain inside the material, and that pulse is in form of electric pulse, and that pulse we can easily sense with the help of very simple sensor in form of a signal. So when we apply electromagnetic field over the material, then this magnetic field will disturb the magnetic domain and we will get a pulse. This pulse is very important to assess the quality control of manufactured product. You may be knowing that in old days, the doctors used to assess the health of the patient by measurement of this pulse. This pulse is very important to monitor the health of patient. Similarly, we can say that the pulse that is generating from the material is also very important to assess or to judge the quality of component. This pulse is generating because of the random motion of the magnetic domain. You can see this is the simulation of random motion of magnetic domain inside the material. And this random motion of the magnetic domain inside the material is generating a burst type signal that you can see at the right hand side of the screen. This voltage pulse or voltage burst we can envelop in a curve, red color curve, so that we can analyze the various process parameter of this red color envelope. Now, this burst or this signal was first discovered by Professor Heinrich George Barkhausen. He was German professor, very well-known scientist. In the memory of Professor Barkhausen, German released a stamp, and first he discovered this signal with the help of a very small loudspeaker. You can also go through the experiment of Professor Barkhausen in YouTube. Just type in the Google or in YouTube Barkhausen noise setup or Barkhausen noise experiment. Basic Barkhausen noise setup or basic Barkhausen noise experiment. You can easily see the electromagnet connection with the loudspeaker, and when the iron bar inside the coil, if you are moving, you will get the rushing sound from the loudspeaker. So this setup you can use for your undergraduate project or postgraduate project to your student. It is very good, and this can be a UG level project also. So this signal was assessed by Professor Barkhausen with the help of loudspeaker. So that signal name is Barkhausen noise signal. So this signal is captured, and then with the help of an envelope, we characterize this. We can characterize this envelope by its peak value or by its peak position. So suppose we are having a graph, and on this graph we are having on x-axis applied magnetic field, that is the input, and if we are having y-axis, that is having Barkhausen noise signal magnitude, and if we plot this graph, then this curve is having peak value and peak position. Now, suppose we are having two components. Suppose we are having two components. This component is having low hardness, and this component is having high hardness. So, what will happen if the component is having low hardness? Then its grain size is very small. According to Hall-Patch equation, hardness is indirectly proportional to the grain size. I repeat, according to Hall-Patch equation, grain size and hardness are inversely proportional. So if this component is having large grain, then its hardness will be low. Large grain means a small grain boundary. Then if I apply Barkhausen noise technique over it, suppose this is the signal that you are getting from this component that is having low hardness. Again, if I apply this technique over this component which is having high hardness, then the signal will come like this. Reduction in amplitude or reduction in peak value will indicate the hardness value, because large grain in high hardness component, a small grain in high hardness component will act as a barrier or will act as a speed breaker for the motion of magnetic domain wall. That is why the peak value will decrease, and we will get this small signal from the high hardness component. So we can assess the micro hardness or bulk hardness of the component within 1 minute or within 2 minutes by using this technique. Now, suppose we are having two components. One component is austenite or ferrite. One component is ferrite. Ferrite is very good magnetic material. And another component we are having martensite. And this martensite is very hard to magnetize. So one side we are having a material which is very hard to magnetize. Another side we are having a component that is having ferrite. And this component is easy to magnetize. So this easy to magnetize component is having this graph. In this case, graph is having this applied magnetic strength or this applied magnetic field required for magnetization. So this ferrite component or ferrite based component is having this graph that you are looking at the screen, and it is having a certain amount of applied magnetic field or input. Now, if I apply the Barkhausen noise technique over this component which is having martensite or hard to magnetize, then in that case, large amount of magnetic field will be required to magnetize because this is hard to magnetize. So this will require more amount of magnetic field. So I will get more amount of magnetic field on x-axis. So the peak position will indicate the microstructure, stage analysis. So by using this technique, we can assess grain size, we can assess micro hardness, we can assess microstructure, as well as we can also assess the residual stress with the help of this technique. So this technique is based on magnetism. So in case of magnetism, magnetic domain wall will move, and this motion of magnetic domain wall, when it will move inside the material, this motion of magnetic domain wall always occur in two paths. First path is magnetization, second path is demagnetization. So you can see that the curve which is having two paths, first one is the magnetization, second one is the demagnetization. This is a closed loop, and this closed loop is having name hysteresis loop of magnetization. And this each path, whether it is magnetization or demagnetization, it will generate Barkhausen noise signal. So magnetization process will generate a Barkhausen noise signal, as well as demagnetization process will also generate Barkhausen noise signal. We can play with the frequency of applied magnetic field. If we change the frequency of applied magnetic field, we can change the strength or we can change the penetration of magnetic field as per our requirement or as per the property of workpiece material. Now, hysteresis loop is also very much important. Hysteresis loop is generating because of motion of magnetic domain inside the material. So here in this graph, you are having flux density over y-axis and applied magnetic field strength over x-axis. And these circles are indicating the motion of magnetic domain wall when we applied magnetic field. So when we applied magnetic field, then all the magnetic domain inside the material, they will move and they will move to acquire the stability criteria. They will achieve this stability criteria when they will become aligned in the direction of magnetic field. So you can see that in the first circle, all the magnetic domains are randomly oriented, and when we apply magnetic field H, then this H is having a direction. The direction of magnetic field has been indicated by an arrow. So when the applied magnetic field is increasing, the magnetic domain wall are moving and they will try to align themselves in the direction of magnetic field. At last, when they will become in alignment with the magnetic field, this state is having name saturation state. After this stage, if we increase the magnetic field, then nothing will happen because already saturation state has come or has arrived. So after this, if we increase the magnetic field strength, nothing will happen because achievement of stability has occurred. So this loop is having two paths, magnetization and demagnetization. And this hysteresis loop crosses x-axis and y-axis at 2 points. So you can see that this red color loop is crossing x-axis and y-axis at 2 points. And these intersection points provide very important magnetic property. These magnetic property we can easily correlate with the mechanical property. So by using or by assessing these magnetic property, we can assess the mechanical property. Mechanical property we can assess in terms of microstructure, micro hardness, residual stress, surface roughness. All these mechanical property are related with the quality, and we can judge the quality of the component by assessment of these magnetic property. This is a very important information that we can derive from this hysteresis loop. This graph is having two hysteresis loops. So the first graph or the narrow graph is coming from soft magnetic material, and the wider graph is coming from hard magnetic material. So you can see that if the material is soft, then it is generating very narrow hysteresis loop, and if the component is hard, then wider hysteresis loop we are getting. And these will indicate the magnetic property because of the intersection point of these graphs on x-axis and y-axis are different. So we can assess these magnetic property to judge the mechanical property or quality of the manufactured component. So we have derived a connection between mechanical property and magnetic property. So these magnetic properties are having direct connection with the mechanical property to assess the quality control in manufactured component. And you know very well that in case of X-ray diffraction technique, we are using X-ray, and this X-ray is harmful. You have also having this experience whenever you are going for health checkup, for X-ray checkup, the person who is taking the X-ray, he also cover himself in a shield, and that shield protect him from the harmful effect of X-ray. So X-ray is harmful for our body, and that is used in case of X-ray diffraction technique. But in case of this technique, micromagnetic technique or Barkhausen noise technique, it is not harmful, because if I keep the permanent magnet for few hours in my hand, nothing is going to happen. Nothing is going to happen with my health. But if I expose my body towards X-ray, then it is definitely detrimental or harmful for my body. We have seen that Barkhausen noise technique or micromagnetic technique is generating Barkhausen noise signal as well as hysteresis loop. Hysteresis loop is having two paths. One is demagnetization, another is magnetization. So each path, whether it is magnetization or demagnetization, it will generate Barkhausen noise signal. So you can see in this slide that two paths are there. First one is the demagnetization path, another one is the magnetization path. In magnetization path, you are having 4 points A, B, C, D. For each path, we are having Barkhausen noise signal. So you are having this information in the slide that a hysteresis loop which is combination of magnetization process and demagnetization process, it is having two signal, and this signal is the Barkhausen noise signal. So if we consider the generation process, or if we consider the generation of Barkhausen, then we have to see this example. This example is nothing but it is the effect of magnetic field by a permanent magnet. This permanent magnet is having north pole and south pole, and this permanent magnet is suppose having a alpine. Alpine I am considering because it is having a head or tail. The alpine is having a head and alpine is having a tail. So if this alpine that is made of iron, if this alpine is within the magnetic domain or within the effect of magnetic field, then what will happen? First, this alpine, this will become active. Okay. So initially, this alpine will move little bit. This movement or this energetic period of alpine is having name elongation. This elongation of alpine, again I repeat, this elongation of alpine requires some amount of magnetic field that you have seen in case of this hysteresis loop. Point number A to B, I repeat, from movement of point A to B is elongation path. This elongation path requires some amount of input in form of magnetic energy. And this A to B path in hysteresis loop has been shown by large distance. It means it requires large amount of magnetic field. And this large input is generating very small noise signal that you can see in case noise signal. A to B is very small contributor in case of Barkhausen noise signal generator. Second, what will happen after this elongation or after this activeness or energetic period of alpine? This alpine will be attracted towards the permanent magnet. So you have seen the motion of alpine towards the magnet. This motion is indicating path B to C, from point path B to point C. This is magnetic wall movement. And you can see that in this B to C path, very small amount of magnetic field has been acquired. So this requires very small amount of input in form of applied magnetic field. And this path B2C is generating large amount of magnetic field, or it is the main contributor in generation of Barkhausen noise signal that you can see here. But after this, the alpine will not stay in this position. The alpine will always rotate itself in the direction of magnetic field. So this is the rotation of magnetic field, or this is the rotation of alpine, and this rotation has been indicated by C to D. So this C to D rotation of domain wall will contribute very significantly in case of Barkhausen noise signal that you can see in Barkhausen noise signal graph. So we are having three paths: elongation, domain wall movement, and rotation. All these paths are very important for assessment of residual stress. So this is the Barkhausen noise signal and hysteresis loop. And this hysteresis loop is having intersection point at x-axis and y-axis. These intersection points are having name remanence, coercivity, and the remanence and coercivity. These are magnetic property. So you can see the location of remanence and coercivity in this graph. The intersection with y-axis is remanence, and the intersection with x-axis is coercivity. These magnetic properties are related with grain size and hardness. These are the mechanical properties. So by assessment of these magnetic property, we can assess grain size and hardness, as well as if I draw a tangent at the knee of hysteresis loop, then this tangent, the slope of tangent will indicate the permeability, and hysteresis loop area. I can easily find out the hysteresis loop area by using any software like PDF, like Microsoft. This area will indicate the microstructure. So all these mechanical property I can assess by this hysteresis loop, and residual stress can also be assessed if we compile all the discussion that we have carried out till now. In the discussion that we have carried out in 1 hour 15 minutes, what is the indication? When we are having a magnetic field, this magnetic field, if we apply over a material, this magnetic field supply the magnetization energy to the domain wall of the material, and this energy will energize these domain wall, and they will first try to move in form of elongation. So this is the first stage of motion of domain wall, that is the elongation. Second is the domain wall movement. So these domain wall movements we have seen in case of alpine and permanent magnet example. And then the domain wall will rotate to align themselves in the direction of magnetic field. So this block diagram is providing very important information that if we supply magnetic field, it will provide magnetization energy for motion of domain wall in three stages or three steps: nucleation, magnetic domain wall movement, and rotation. So if we are having magnetic field, this magnetic field will be divided into three parts for magnetic domain wall motion. Now, if the component is having, suppose the component is having grinding operation. I repeat, the component, if this component is having grinding operation, then we have seen in case of grinding, it will induce tensile residual stress. So this component, this is having grinding operation over it, and this grinding operation will induce tensile residual stress. It means it will elongate all the things. It will elongate void that we have seen in the schematic diagram. This tensile residual stress will elongate porosity, cracks, as well as this tensile residual stress will elongate the magnetic domain wall. Okay, I repeat, the tensile residual stress that has been induced by grinding, it will elongate porosity, it will elongate void, it will elongate grain size, it will elongate crack, as well as it will elongate the magnetic domain wall. So when the component is having grinding operation, this component, nucleation part or elongation part, this has been carried out by the grinding operation itself. Now, if we apply the same magnetic field over it, then this complete magnetic field will be distributed only in two components. That is magnetic domain wall movement and rotation, because the elongation part has been covered or has been executed by the grinding process itself. So in this case, in grinding, the domain wall is already strained to elongation, and the magnitude of Barkhausen noise signal in case of infection of ground component after grinding, the Barkhausen noise signal level will rise. So qualitatively, we can easily assess the amount of residual stress in manufactured component by using this technique that is very useful nowadays. So this technique will provide the information regarding the residual stress, whether it is increasing or decreasing qualitatively. And this information is very much useful, and the technique is very much preferred in research and development sector, because this is emerging technique. This emerging technique is supporting the environment because it is not using any chemical. We are using the chemical in case of metalography technique. We are using the etchant. We are using the polishing agent in case of etching. In case of micro hardness analysis or metalography analysis, these agents and chemicals are not good for the skin of the operator or not good for the environment. And X-ray diffraction technique is also using X-ray, that is not good for health of the operator. But this technique is only using magnetic field, and that is not having any harmful effect to the operator or to the environment. So this is a barcode and noise analyzer that you can see here in this screen. So this is a box type instrument, and this box type instrument is having weight around 7 to 9 kg. So you can easily carry this instrument to field application, or you can use this instrument in your laboratory also. If you are in teaching the field, then you can provide the UG level project or PG level project by demonstration of Barkhausen noise signal using the electromagnet yoke and sensor. I have also given the same problem demonstration of Barkhausen noise signal to my student. My MTech student has demonstrated this, and the cost of setup was 2,753 rupees. I repeat, in 2,753 rupees, we have demonstrated the generation of Barkhausen noise signal by using a very low level setup, that is a magnetizing yoke and a electromagnet and a loudspeaker also. So you can also use this information. You can also use the information available on the YouTube or on the Google to prepare the setup for this Barkhausen noise signal generation, and it is very good. It is also very learning experience for your student also. So these are some instrument, some screenshot of Barkhausen noise signal analyzer. This analyzer is having static loop. So this will also provide the information regarding the coercivity. You can see that coercivity is there, remanence is there, permeability is there, and area under the static loop is there. So all these magnetic property you can correlate with the mechanical property, and you can assess the quality of manufactured component. So this is the actual graph, experimental graph between the residual stress and a grinding operation. In this grinding operation, the downfeed or depth of cut was varied. So this downfeed, when it was varied, it is indicating that thermal damage was more. We came to know that in case of grinding, thermal damage is quite high because of negative rake angle, because of spark, because of low thermal conductivity of alumina and silicon carbide. That is why thermal damage will increase with increase in depth of cut. And that you can see in case of this graph, it is indicating that amount of residual stress is increasing from minus 200. Minus 200 means it is compressive. And that it is increasing up to 600 megapascal. It is very, very high amount. 600 megapascal is very high. It is indicating a very severe thermal damage in the ground component. So these are the various graphs between X-ray diffraction technique data and Barkhausen noise technique data. So you can see that a very good correlation has been obtained between the result from Barkhausen noise technique and X-ray diffraction technique. So these technique has established its usefulness in measurement of residual stress in comparison to accreditation technique that you can see here. So this is all about the Barkhausen noise technique or this useful technique that is preferred nowadays. It is a emerging technique in industries. It is emerging technique in modern manufacturing industries for micro level characterization of component for assessment of quality. And this technique is also available in India. IIT Kharagpur is having this technique. BARC BARC Mumbai is having this technique. IG Car Kalpakkam is also having technique. Industries like Bharat Forge is also having this technique. So in India also, 10 to 15 industries and teaching institution is also having this technique. You can also develop this technique. Available setup is available in the YouTube, and it is a good learning experience for you also. So that is all from my side about this technique, emerging technique. I have also used this technique, the barcode and noise technique version I have used in IIT Kharagpur, and I have also used the same higher version at Newcastle, England during my postdoc there. So that is all from my side. If you are having any query, you can raise your query, Harry, or you can use my email ID. If you are having any query regarding this, I will try my best effort to satisfy your query. Dr. Manoj, that is over. That is all from my side.
If you anybody have any query, please ask.
If anybody wants to ask question, please raise your hand. If
Okay,
Hello.
if you are not having any query, you can use my email ID. Okay, you are having
Sir,
some query. Yeah.
sir, myself RP Singh from IPS College, Associate Professor, Mechanical Department. Sir,
Okay.
there is my query. What I found during our industrial visit, Sitholi Railway Spring, what we found, there was a intentionally production of residual stresses on railway spring
Okay.
by short pinning process.
Yes.
They
Yes.
were they were inducing compressive residual stresses
Yes.
to
Yes.
enhance the fatigue life. Okay, sir.
Yes.
Uh, but what I found, when the spring is working, when the rail is going on the track, uh, there must have been some sort of tensile forces or compressive forces, both on the spring.
Yes.
So to
Yes.
certain extent, residual compressive strength may enhance the fatigue life. But don't you think that there would also be some sort of tensile residual stresses generated during that?
Yes, you are absolutely right, Dr. Rajesh. In case of manufacturing, we intentionally create compressive residual stress. You are going through
Right.
short pinning operation, even grid blasting operation is also there. By using grid blasting operation or short pinning operation, we intentionally induce surface finish will be definitely poor, but we are not bothered about the surface finish that is going to be distorted by short pinning or that is going to be distorted by grid blasting. We are interested in induction of compressive residual stress. This compressive residual stress will increase the fatigue life and the static strength of the component, because what is happening, it is blocking the enlargement of impurities or discontinuities. It is blocking the enlargement of porosity, crack, void inside the material. But in case of their field application, when they are exposed to the heavy load condition in environmental effect, the railway track is having spring component that is exposed in daylight, also that is exposed in night time. So temperature difference there, and each material is having thermal expansion and thermal contraction. So in this
Right,
duration of
sir.
4 hours, and you are applying heavy load. So because of this heavy load and temperature variation, the amount of compressive stress it reduces, and in this field application of heavy load condition, it induces the tensile residual stress. So we have to keep
Yes.
monitoring. You have seen the continuous monitoring operation of railway track. It is because of this variation in load and daylight duration.
Right, sir. Right, sir. Sir, my one more question, please, sir. As you
Yes,
explained
you are.
in magnetizing process of hysteresis curve, basically we
Yeah,
have three types of magnetic material: para, dia, and ferro. Right, sir?
yeah.
So
Bilkul, absolutely right.
the effect you explained basically means for para material, na? Because on dia material this won't be applicable. Am I right?
Yes, you are absolutely right, Dr. Rajesh. Again, your question is very valid regarding this presentation. It is very valid question. What is happening? This technique is applicable on those materials which are having magnetic domain. So,
Yeah.
paramagnetic materials are there, diamagnetic materials are there, ferromagnetic materials are there. So, this technique is only applicable to ferromagnetic component. Okay, it is not applicable to diamagnetic. It is not applicable to paramagnetic, because they are not having magnetic domain which are having motion capability. But we are having a component that is having name steel. In case of steel, in case of medium carbon steel, in case of mild steel, in case of high carbon steel, they are ferromagnetic in nature. So majority of the component that we are having nowadays, they are magnetic in nature. Suppose the component that you are going to manufacture, it is made of copper, then this technique is absolutely not applicable. If you are having any component made of aluminum, this technique is useless for that. So this technique is having some advantage, and the biggest disadvantage or limitation, it is only applicable to ferromagnetic material, but still comes under the ferromagnetic material. Very good question from Dr.
Right,
Raj.
sir. Right, sir. Thank you, sir. Thank you very much, sir.
Okay, okay. Welcome.
Okay.
Good evening, sir. Good evening, sir.
Good evening.
Prem Prakash Pandit, Assistant Professor, Department of Mechanical Engineering. Sir, I want to ask one question. Sir, which microscopic techniques are most effective for studying microstructure study?
Yeah, if you are going for ferrite, okay, ferrite is very good. Suppose you are having a mild steel component, it is made of ferrite and perlite. It is good for study. If you are having medium carbon steel, that is AISI 1060, it is also good because it is having some large amount of ferrite component. Ferrite is very good. Ferrite is very easy to magnetize. So if any component, any steel, it is having ferrite or large amount of ferrite, it is good. But martensite is very difficult, very hard to magnetize. So if the component is having high carbon, high martensite, it is very difficult. So it is not going to easy to use this technique for the magnetic, for the material which are hard to magnetize. And austenitic stainless, it is no, because it is not ferromagnetic. Okay. So the component which are having good amount of ferrite, large amount of ferrite, they are good for analysis by Barkhausen noise technique. And the component which are having large amount of martensite, very difficult to magnetize, very hard to magnetize, are little bit difficult to analyze by this technique, because the Barkhausen noise signal that will be generated. In case of ferrite, this much amount of burst you will see, this much amount of burst. But in case of martensite, this much amount of burst you will see. So it is difficult to analyze. And the component which is having austenitic, it is not applicable for this technique. Okay.
Thank you, sir.
Any good question? Good question.
Actually,
Any
sir, there
other?
are many microscopic techniques are available like SEM, TM, and
अरे
AFM.
वाह, good, very
So
good.
I'm
अगर आपके पास
curious
SEM
to which technique is so best for study?
हाँ, तो आप देखिए माइक्रो स्ट्रक्चर की क्या होता है, जैसे अगर आप कुछ टेक्निक्स होती हैं जो जर्नल्स मानते हैं डेकोरेटिव टेक्निक्स है, जिसमें कुछ कहती है कि आप एसईएम करिए, टीएम करिए। लेकिन अगर आपकी मेट्रोग्राफी स्टडी पे, मेट्रोग्राफी एनालिसिस पे आपकी पकड़ अच्छी है, आप माइक्रो स्ट्रक्चर अच्छी तरह एनालाइज कर सकते हैं, उसके फीचर को आप अच्छी तरह स्टडी कर सकते हैं। तो सिंपल मेट्रोग्राफी स्टडी से निकले हुए कुछ पेपर मटेरियल में देखेंगे, जेएमईपी में देखेंगे, आईजेएमटी में देखेंगे, उन्होंने एसटीएम टीएम नहीं किया था, लेकिन जो इन्फॉर्मेशन उन्होंने ऑप्टिकल माइक्रोस्कोप से मेट्रोग्राफी स्टडी से एक्वायर की थी, वो इतनी रेलिवेंट थी कि उनका रिजल्टेड डिस्कशन पार्ट काफी ब्यूटीफुल हो गया। और अगर आपके पास सारी इन्फॉर्मेशन ऑप्टिकल माइक्रोस्कोप से आ रही है, आपको सारा माइक्रोस्ट्रक्चर ग्रेन साइज पता पड़ रहा है, तो फिर अगर आप एसटीएम या टीएम पे जाते हैं तो वो सिर्फ डेकोरेटिव पर्पज के लिए होगी। बाकी इन्फॉर्मेशन तो सेम आपको वही मिलेगी जो आपने माइक्रोस्ट्रक्चर से निकाला है। हाँ, कई जगह आपको एसईएम या टीएम करना पड़ता है, जैसे कई जगह क्वेश्चन आता है डिसलोकेशन डेंसिटी, तो डिसलोकेशन डेंसिटी फाइंड आउट करनी है, तब आप जा सकते हैं एसईएम पे या टीएम पे।
Thank you so much, sir.
ओके, गुड।
Any other? Okay. Thank you, sir. Now I invite Organizing Secretary, Mr. Vinit Raj Singh Kushwaha, to propose vote of thanks.
Good evening, everyone. I, Vinit Raj Singh Kushwaha, on behalf of the organizing committee of the 1-week faculty development program for recent advances and applications of manufacturing in Industries 4.0, extend my deepest thanks to the eminent keynote speaker, Dr. Meghanshu Basist, Associate Professor, IIT BHU, for delivering such an insightful and inspiring keynote address today. Your expertise, passion, and vision in micro-characterization of material upon machining have provided us with valuable perspectives, and it will definitely influence and inspire our future endeavors. We appreciate you, how skillfully you highlighted manufacturing process, characteristics of grinding, hysteresis loop, and various analyzers, and connected them to the current challenges and opportunities. A big thank goes to the participant also for making it interactive and enthusiastic. Thank you all once again.
Thank you, sir.
Okay.
Thank you, Ashish, sir.
Okay. So thank you to all again. And so now I am leaving. Okay.
Okay,
sir.
sir.
Thank you so
sir,
much, sir.
for
Thank
taking
you,
out
sir.
time in your
Thank
busy
you.
schedule.
Thank you. Thank you. Okay.
Okay.
Thank you, sir.
Okay.
The feedback link will be given. Dear participants, the feedback link will be given at the end of the today's program in chat box and WhatsApp group. Please fill and submit it by tonight up to 10 p.m. It is mandatory for all participants to submit feedback for the attendance purpose. Otherwise, you will be considered absent. So now we are proceeding for our next session. Sir has joined. Jain sir. Okay.
Yeah, I am here.
Good evening, sir.
Good evening.
Good
Very
evening,
good evening, sir.
Very good evening.
Good evening, everyone present over here. So now we will proceed for our next session. I invite Dr. Ankur Jain, Associate Professor, NBARD, Hiroshima University, Japan, to deliver his talk on advanced materials and nanotechnology in manufacturing. But before this, I would like to take the privilege to introduce our next speaker, Dr. Ankur Jain. Dr. Ankur Jain is currently a head Center for Renewable Energy and Storage and professor in physics, Suresh Gyan Bihar University. Sir did his BSc, MSc and MPhil from Dr. Bhimrao Ambedkar University, Agra in year 2000, 2002 and 2003 respectively. Sir did his PhD on title Investigation of Hydrogen Storage in Zirconium and its alloys from Center for Non-Conventional Energy Resources, University of Rajasthan, Jaipur in 2007. Sir has 21 years of teaching and research experience. Dr. Jain has published 100 plus publications in SCI or Scopus journals and 20 chapters in books published by international publishers. Sir has received different fellowships from various funding agencies from India and other countries. Sir has different academic responsibility, like he is a director IQAC. He is head Center for Renewable Energy and Storage. He is a leader for Criteria 2 for NAC accreditation. He is a coordinator, PhD coursework e-content preparation. He is a convener, Board of Studies, Physics and Energy. He is DRC convener, and he is member of National Educational Policy Implementation Committee. Now, it's time to hear from our speaker, Dr. Ankur Jain. It's over to you, sir.
Thank you, madam, for nice introduction. So before starting my session, I would like to thank Dr. Manoj for inviting me here in this FDP program. Today, I'm going to talk about advanced material and nanotechnology in manufacturing. So I was working for quite a long time at Hiroshima University. This is our center name, Natural Science Center for Basic Research and Development, where we were engaged with the material related research. We were doing the research on hydrogen energy materials. We were also working with the battery materials. Recently, I have joined Suresh Gyan Bihar University, as Madam has recently introduced. So today I am going to talk in 4 different sections. which is relevant to the topic of this FDP. Section 1, I will tell briefly about advanced materials. Section 2 will deal about nanotechnology and nanomaterials. Then section 3 will be about the use of nanotechnology in various industries. And finally, I will discuss about our recent works, what we are doing towards energy storage materials. So let me start with section 1, which is related to advanced material. So what is actually advanced material? Advanced material is nothing. These are the materials which are developed through specific techniques, specific synthesis technology, and specialized processes with several beneficial properties. They are very noble. They have improved properties in comparison to their benchmark material or their parent material, such as they have better weight, they have better strength, they have better conductivity, and there are a lot of many other properties which are needed for different applications. These are some examples of advanced material. According to the use, for example, if we want to use light metals, we can develop a special material based on titanium. We can develop materials based on magnesium, aluminum. Recently, we have developed several composite materials which are quite strengthened and they are also lightweight. For example, carbon fiber is a good example of this. There are several nanomaterials, nanocomposites. Steel is quite conventional technology. However, there are several new materials based on steel has been developed and that are classified inside in the advanced material. And apart from these light metals, composite or steel, there are several other materials which can be developed for specific applications. Why they are, what is their place in manufacturing industries? They have several improved properties. These are the examples. And actually, if I talk about particularly two industries, for example, automotive and aerospace industries, they are facing a lot of challenges and there is a need for improved fuel economy. If you make very lightweight aerospace things, then it will improve the fuel efficiency. They will improve overall performance and they will reduce overall carbon emission or carbon based gas emissions. Okay. We also, in addition, we also need very lightweight body structure. So these materials are very important for our several applications. For example, there are some benefits. If I talk particularly about magnesium, this is comprised of, there are several composites, there are several materials which can comprised of magnesium, and this magnesium is actually having the weight only 22% of iron and 65% less in comparison to aluminum. So but even if they are lightweighted, they are very, very much strong in comparison to steel. They are almost 50% of the strength of steel, but they are lightweight also. Right now, the magnesium based market is almost 450,000 tons per year, and it is continuously increasing by 5%. So magnesium is quite attractive material. This is quite lightweight also. Again, same material is titanium, which is very much strong as similar to steel, but the weight is quite smaller than steel. It is only half of the weight of the steel. And also, in comparison to steel, it is also corrosion resistant. So there is no problem of corrosion. This has very high melting point also, and that requires specialized machining and annealing process. So that the market for titanium is also growing very fast in recent years. Then other example is carbon fiber. This is again lightweight material, which is 75% lighter than steel, but it is high stiffness. The Young modulus is also quite high, that is up to 300 gigapascal. That is 12 times of steel, and this is more durable also. So these are some of the benefits. Very recent example, there are several materials which has been developed in the category of nanocomposite. They have 98% stiffness improvement, they have higher heat deformation temperature, and several other benefits are mentioned on this slide. Now, I will come to the next section, which is related to nanotechnology and nanomaterials. So what is the nanotechnology actually? Nanotechnology is nothing but that refers to the construction and engineering of the functional system at atomic level. Actually, it is written here at very micro level. That is not a literal meaning of micrometer size, but that means to say that when we are dealing with the material on atomic level, that is termed as nanotechnology. Nanoscale materials are defined as a set of substance where at least one dimension of that material is less than 100 nanometer. So whenever we talk about 500 nanometer or 600 nanometer, remember that is not classified as nanomaterial or nanotechnology. The dimension should be smaller than 100 nanometer. This nanometer is 1 billionth of a meter, 10 to the minus 9, and nanometer is 1 millionth of a millimeter, which is approximately 1 lakh times smaller than the diameter of human hair. So this is the beauty of nanotechnology. The concept was first presented in 1959 by Dr. Richard P. Feynman. Then the well-known term of nanotechnology was coined by a Japanese scientist, Norio Taniguchi, in 1974. And with the invention of scanning tunneling microscope in 1981, which is capable to observe the nanostructure in true sense, which was discovered in 1981, that makes the market very emerging. That is the beginning of the emergence of nanotechnology. These nanomaterials can be divided into three major categories. First one is one-dimension material. This has only one parameter. Either it can have length, it can have breadth or height. So length, breadth, or the height. The dimension should be, as I told earlier also, the dimension should be less than 100 nanometer. Then only it will considered as one-dimensional nanomaterial. The second category is two-dimension, where it has two parameters. One is length and another one breadth, and both of the parameters should have in the range of 100 nanometer, or at least one dimension should be less than 100 nanometer. Then only it will considered as two-dimension nanomaterial. Then third category is three-dimension nanomaterial. It has all the parameters of length, breadth, and height. All the three dimension can be smaller than 100 nanometer, or at least to qualify the definition of nanomaterial, it should have at least one dimension which should be less than 100 nanometer. What are the properties? These nanomaterials can show different properties at nanoscale for two different reasons. The first one is nanoparticles can make materials which are more chemical reactive, and they can affect their strength or electrical properties. And second is quantum effect that can begin to dominate the behavior of matter at nanoscale. So actually the properties of nanomaterials are quite different from the bulk material. A bulk material should have constant physical properties in general, but when it comes to nanomaterial, the properties can be drastically changed. Okay. Then to understand this nanoparticles or nanotechnology, there is an important parameter, surface area to volume ratio. We can understand from this figure. Here I am showing two blocks. One is a complete block and one is a set of 8 different blocks. If we calculate, the surface area is related to height into width into number of sides into number of cubes. So for this, we have total number of sides is 6 and number of cube is 1. So the volume will be volume equals to height into width into length into number of cubes. So for example, if we talk about the left hand side cube, the surface area is 2 into 2 because the length and width is 2 mm and 2 mm, that is 2 into 2, and total faces we have 6 and the number of cubes is available 1. So the total surface area in millimeter will be 24. Whereas if we talk about the right hand side image, we have total 8 cubes and the dimension of one cube is 1 millimeter by 1 millimeter. So that will give us 1 into 1 into 6 into total 8 pieces. That will give us 48. If we talk about volume, volume will be height into width into length into number of cube. For this cube, it will be 2 into 2 into 2 into 1 cube. So that will give us 8. However, in this case, it will give, because we have only one cube of dimension 1 millimeter. So 1 into 1 into 1 into total pieces we have 8. So the volume will be 8. If we calculate the surface area to volume ratio, it will give, for this single cube, it will give 24 divided by 8. That will be 3. However, Now we are splitting the same cube into 8 pieces. In this one, it will give the surface to volume ratio will be 48 divided by 8. That will be 6. That means when we break this whole cube into 8 different pieces, the surface area to volume ratio is increased. And that increase in surface area to volume ratio drastically change the properties, and that result into different properties, including catalyst, because we have larger surface area to give the reaction in a greater extent. Okay, this nano size effect, they can affect several properties. For example, physical properties including melting point, chemical properties, for example, reactivity. They can also modify electrical, mechanical, and optical properties as well. Why this variation in properties happen, that can be understood on the valence bond model, band theory. If you talk about bulk metal, the conduction band overlap with the valence band. They are close lying band, and the unbound electrons, they have the motion that is not confined in these bands. But when we decrease the size, there is a gap created between the conduction band and valence band. There is a separation created into these two banded, and then electron motion becomes confined. And that originated the quantization sets in. Now these properties, how they vary, we can take an example of gold, which is very good example for nanocatalyst. If we talk about bulk gold, this is shiny yellow metal, but when we reduce the size of gold particles, the nanoparticles appear red in color. Now the bulk gold, they does not have any catalytic properties. However, when we go down to gold particles of the size 30 to 500 nanometer, that shows excellent low temperature catalyst. So this is the beauty of nanomaterials and nano technology. There are 4 important parameters to define the nano material, nanotechnology. These are size. When we reduce the size, it terms as nanotechnology. Where there are several shapes available. There can be nanosphere, nanoplate, nanocube, nanorods. These are some examples of material. The types of material, the morphology of material. There are, for example, metal particles available. There are hydrogel particles available. There are polymer particles, liposome, carbon nanostructure. So there are multiple morphologies available for the nanomaterials. And these are the surface properties which is listed here. Now, what is the use of nanotechnology? Because this FDP is focused on the use of nanotechnology and advanced material in the industry. So this section will briefly describe how this nanotechnology is being used in different industries. So here is the list of the industries where nanotechnology is being used, starting from food industry, agriculture industry, oil and gas industry, consumer goods industry, aerospace industry, chemical industry, construction industry, nanotech in biotechnology, nanocomposites, electronics industry. So you can see here, there is no industry left behind which is not using the nanotechnology in any of the aspect. Or even the energy sector is not untouched from the nanotechnology. Nanotechnology can be used for energy production, energy saving, energy distribution, as well as energy storage. So I will briefly introduce how this nanotechnology is important for different industries. First, we will talk about food industry. The main areas in the food industry is to change the food characteristic, is to package food using nanotechnology, and to produce food, and also the processing of this food. Very recently, a very nice terminology is evolved that is not called nano food. So nano food is not the only the nanoparticle which is to be eaten, but the preparation involved the nanotechnology, and that's why it is called as nano food. So that means the nano food is defined as the food which is using nanotechnology techniques or nanotechnology tools, starting from cultivation, production, processing, or packaging. Here you can see is more precisely, you can start from agriculture. So nanotechnology is there, then the processing of food, nanotechnology is again there, and finally when we receive the products, there is UV production or antimicrobials conditions and abuse monitor, they all are now dependent on the nanotechnology. And that's why food industry is also being dependent on nanotechnology these days. Now, second part, agriculture, which is again partially discussed in previous slide. Now, to make farming more precise, we are using nanotechnology. There are nano delivery systems which are really advantageous for the agriculture industry. Now, third one is oil and gas industry, where we are using a lot of applications such as sensors, coatings, nanomembranes, nanofluids and nanomaterials for drilling and completion. So these are some of the aspects which are being used for oil and gas industries these days. Now, the next one is consumer goods industry. The areas of application are including surfaces and coatings, textiles, cosmetics, and sports. The next one, aerospace industry, where I have shown, when I was showing the example of advanced material, I have shown that titanium is one of the material which can replace steel because it is being a lightweight material and it is more stronger than steel. So here is the advantage. For example, in aerospace industry, we can build nanostructured metals, we can create polymer nanocomposites and also tribological and anti-corrosion coatings, which will be helpful for the aerospace industry. The chemical industry, again, one of the very good example, one of the very good application is related to catalysis process. When we are lowering down the size of any material, it can work as catalyst for one or other application. So this is possible, and you can see platinum is one of the very good example. Platinum nanoparticles are being considered in almost every second catalysis application. Okay, now come to construction industry. Now we are producing cement, we are producing steel, we are producing glasses using nanotechnology again. They have potential to make construction faster, cheaper, safer, and more varied. Now, nanotechnology in biotechnology. Biotechnology is itself a refined form of biology. And when it combines with nanotechnology, it has several other advantages. For example, drug targeting, accumulation at higher concentration than normal drugs. They have increased permeability, they have selective localization, and they also have overcoming the presence of blood-brain barrier. Further, there are some diagnostic applications. We are using nanotechnology in detection, individual target probes. We are using them for protein chips. We are also using this nanotechnology in the imaging tools. Then therapeutic applications, we are using nanotechnology in drug delivery, gene delivery, biomolecular engineering, biopharmaceuticals, as well as several drugs also. Because nanotechnology at one side is very beneficial, however, there are certain hazards also, which are really important to talk when we are talking about biotechnology. There are several hazards. For example, if ingested, the nanoparticles can reach to the circulation and reach different organs, and that can harm very badly to human beings. Okay, so these are some challenges. Exposure to nanomaterials need to be monitored very carefully. We need to develop applicable methods to detect these nanomaterials, predicting effects of these nanomaterials and impact of engineering nanomaterials on health. Then nanotech in composite material. The trend in composite has been to use nanomaterials as a kind of super filler in polymer resins. These polymers can achieve the same performance properties as can be achieved with the traditionally filled resins, but with a smaller filler volume fraction. So that will save the total volume of the utilization. Okay. Then there are several applications for these composite materials. For example, lubricants and scratch-free paints, new fire retardant materials, new scratch abrasion resistant materials. They can be used for food packaging. They can be used in other applications as well. Now, if we talk about electronic industries, this is very famous. And actually, the nanotechnology, the use of nanotechnology has drastically revolutionized electronic industries. The main advantage in the coming years will be like flexible electronic circuits, We will have our mobile phones flexible. We can use higher speed data transmission. We can use nanomagnets as switches, and several others we can use in the electronic industries. Okay, now come to nanotechnology use in the energy sector. So energy is quite quite wide field where we can use this nanotechnology. Here I classify this nanotechnology uses according to the type of energy sources. So these are the non-renewable sources of energy, and these are the renewable energy sources. Here it comes to production, and then finally storage. So these are fields where we can use nanotechnology. Here I summarize that if we are talking about energy production, we can utilize it in solar economy, we can utilize in hydrogen economy, we can use biofuels, thermoelectricity. In all the aspects where we are producing energy, we can utilize nanotechnology here. Okay, then energy savings can also be achieved by improving insulation of residential homes and offices, more efficient lighting, and using lighter and stronger material to build devices which would then require less energy to operate. And if I talk about industrially, the main application involve catalysis, advanced materials, insulator, and smart coatings, which can be utilized for saving overall energy of our houses or offices. Then energy distribution is also very important aspect for energy economy. We can replace the current wires which are based on copper mainly, that can be replaced by the quantum wires, or we can call it armchair quantum wires, that can really revolutionize the electric grid. We can improve the efficiency of our electrical conductivity because that is quite high in comparison to copper, almost at 1/6 the weight. This quantum wires are lightweight also. They are stronger than steel, so they can solve many problems which are existing with the copper grid wires. Then we can also utilize high temperature superconductors that can become a superconducting near liquid nitrogen temperature in comparison to conventional superconductors which behave at very low temperature, that is liquid helium temperature around 4 Kelvin. So that can also be developed using this nanotechnology. We can convert the structure into such a structure that can show superconductivity at comparatively higher temperature, and that can be utilized our day-to-day operations. Now comes to energy storage. Nanotechnology can be applied for the field of energy storage because we have a larger surface to volume ratio. The overall energy storage capacity can be increases drastically, and that will help to reduce the overall cost. These are two examples. One is ultra capacitor and second is hydrogen storage. So these are two fields where we can effectively use the nanotechnology. Now, when we talk about nanotechnology or nano materials, it is really important to assess it. It is important to understand the risk involved, and we need to manage those risks effectively. Now, the first thing is assessment. So these are some examples of nanomaterials. The first category is metal oxide. There are several materials which are very famous these days: silicon oxide, titanium oxide, aluminum oxide, and iron oxide, zirconia, and zinc. So the uses of these kind of metal oxide include additive for polymer composite, solar cells, pharmacy and medicines. There are several uses, and they can be used as additives for scratch resistance coatings. The second category is fullerenes that can be used in mechanical and tribological applications. They can be used as additive to grease also. There are multiple carbon nanotubes, carbon nanostructures. Again, there are some categories: single wall carbon nanotubes, multi-wall carbon nanotubes that can be utilized as additive for polymer composites. They can be utilized as electronic field emitters, batteries, fuel cells. And finally, the final field is compound semiconductors, which can actually change the electronic world on optical devices. Now, what are the risks? When we talk about risk, it is actually the main stakeholder are humans and environment. So there are two things where we have to analyze the effect, the risk involved with the human life